A crate hangs from a rope that is attached to a metal ring. Here's the metal ring. Here's the rope. The metal ring is suspended by a second rope attached overhead at 2 points as shown above, What is the angle theta if the tension in rope 1 is 0.75 times the tension in rope 2? The key thing here, or a key insight, is going to be that when we draw a free body diagram, right, so we'll draw our little free body diagram, and we're only going to worry on the ring. The ring must be massless because it didn't give us anything for its mass. So we'll say we'll have F1 pointing that way. And then we know that a rope exerts tensions along its length, in the direction of its length. What's a little weird here is that the rope exerts a tension both this way and this way. And I'm going to call this the tension in it F2, as they said, or as they called it rope 2, so I'll call it. Also, a rope has one tension throughout its length. So these have to be the same, and we're looking for that angle. So that's our free body diagram. And then we say, well, the box is not moving. It's just hanging there, right? It hangs from a rope. And so the acceleration is 0, which implies that the net force is 0. And that gives me two approaches. I could do the actual diagram, or I could do this algebraically. I'm going to do it algebraically first. Plus F1, but F1 points in the opposite direction, so it has to come in with a minus sign, so I'll put a minus there. And then together they have to equal 0 because the y component is 0 because there's no acceleration in the y direction. So we have something like, when we put all of that together, we get 2F2y minus F1 is 0. Let's figure out what that's going to be. So we have over here, we have the actual tension is F2, and I want F2y, and I know that the angle is theta. I should be careful here. Let's draw this a little bit larger and more spectacularly. So, because I want to be able to be clear here. So here is, here is F2, and we have this is the angle theta that we want. So this is F2, and we are looking for F2y. There's, of course, an F2x that I don't care about at this point, but we know that those will be at right angles. So we have that F2y over F2 is the adjacent side over the hypotenuse, which is the cosine of the angle we want. So F2y is F2 cosine theta. All right, that allows us to go back up to that previous equation here, and we can now write that equation as 2F2 cosine theta minus F1 equals 0. And then we have to look at our problem, and our problem told us that earlier in the problem it was said that F1 was some multiple of F2. I don't remember the multiple, and I don't feel like looking it up right now, but at the end we'll put it back in. But it was definitely F1 was some number times F2. So I can put that into this equation and say 2F2 cosine theta minus KF2 equals 0. That allows me to pull out an F2 and be left with, on the inside, 2 cosine theta minus K, and all of that has to equal 0. Now, if two numbers multiply to 0, one of them must be 0, and it makes no physical sense that that be F2. F2 really can't be 0, which means we can divide it out. All right, we can ignore it, and we're left with only that 2 cosine K minus 2 cosine theta minus K equals 0. So cosine of theta is k over 2. So theta is the inverse cosine of k over 2. In our particular problem, we had that theta would be the inverse cosine of 0.75 over 2, which turns out to be 67.976 degrees, which clearly is more like 68.0 degrees, because we won't have too much sig figs. All right, so that's one way to do it. And if you're okay with that way, I think that's the easiest way to do it. But we could also do it more quasi-geometrically, and I'm going to go back and do that now on the next screen. The following is optional. If you're okay with what's been done so far, then you're okay with the problem, but an alternate way of doing it would be to go through the actual triangle. In this case, we have F1 pointing down, and then we have an F2 off to the side. Oops. Like this, and we have F2 coming back, because we know that the whole thing, they all sum to 0. And when three vectors sum to 0, they must form a triangle. Notice it's not a right triangle, although it is an isosceles triangle, and there's probably some stuff we can use for that. Also, the angle they gave us was this angle. That was theta. And we can see that by the idea that when a traversal cuts two parallel lines, it creates alternate interior angles that are equal. This angle is also theta. So we have a triangle. I'm going to redraw that again a little cleaner, like this, like this, like this. And we want this angle, and we know these sides. So like that. One way to do this might be by a law of cosines, which says that the side opposite, F2, it's like a Pythagorean theorem with a correction factor, so it says F2 squared, which is the side opposite, is equal to F2 squared plus F1 squared. Oops, sorry, wrong color. Minus, here, twice their product times the cosine of the angle between them. That is the law of cosines, which hopefully you learned in a geometry class. Now we can simplify it a bit. We can look here and say, hey, look, this F2 and that F2 cancel out. And so we're left with an equation that looks something like 0 equals F1 squared minus 2F2 F1 times cosine theta. And we can factor out and divide out 1 F1, because we could just say this is F1 times F1 minus 2F2 cosine theta. And since F1 can't be 0, we'll cancel that out, and we'll end up with the next line will be that 0 equals F1 minus 2F2 cos theta. But remember, as we had before, that F1 is some constant times F2. So this equation becomes 0 equals K F2 minus 2F2 cos theta, which it should not be too hard to convince yourself ends up being, again, that 2 cosine theta, or minus 2 cosine theta plus K is 0. And that's the same equation as before. So we end up, again, that theta is the inverse cosine of K over 2. Ends up the same place as has to. I think that's geometrically a little bit more complicated to do. But it gets you there, and it's perfectly fine. It's a little weird. This would be the kind of thing that happened whenever you have the isosceles triangles. So there's probably some deep geometric theorem in there too, but I don't know it offhand.